Just introduce myself again in a bit more detail. I see SKF's a big corporation, so job titles change all the time. So actually my current job title is product line manager in SKF's connected technologies area, which is basically where all our condition monitoring technology and other instrumentation systems are all around the bearing business consolidated. And this original invitation was to be presented by one of our UK team, Daniel, but unfortunately he's not available. So they asked me to step in and do this presentation on smart industry solutions. I myself have been in the condition monitoring business for almost just over 30 years now. So I've seen a lot of the, I've seen all of the trends and changes, in fact. So what I'll plan to do in this next 40 minutes or so is just run through the overall big picture and then use some of the technologies that SKF are using in this market as illustrations of how stuff is done. Let's first go on to the first subject, which is smart industry in general. Well, first I thought I'd define what smart is. Where I come from, smart is somebody who's clean, tidy, and well dressed. But these days in industry, the other alternative adjective from North America is more generally used, which is smart means having or showing a quick-witted intelligence, or for devices in specifically, devices that are programmed so as to be capable of some kind of independent action. So that's what we mean by smart. When we look at industry in general, there's lots and lots of buzzwords and terms that smart fits into. It's generally falling into the fourth industrial revolution or industry 4.0, whereas which is the evolution of technology. Most people probably are thinking still the third industrial revolution, which started in the 70s with the use of electronics and computers, the first use of big computers. But today, the integration of devices and computer and internet networks is what's fueling what we call the fourth industrial revolution. And from a plant management point of view, it's all about trying to maximize the utilization of assets and reduce downtime, and it might make maintenance more efficient by using more and more smart information. So more data, more devices, more acquisition units, and more software systems that pull all that together to hopefully achieve a lot of benefits. These pictures that we've pulled together are not SKF's. You can find them in multiple different industry journals and sources. So we're just describing the trend that SKF as a bearing manufacturer particularly is fitting into. Drilling that down in a little bit more detail. So of course we have our planned goals, the plant goals of cost, output, and compliance. So that reflects into a maintenance strategy. So particularly from the mechanical equipment point of view, SKF gets involved at quite an early stage on the actual maintenance strategy of plants. And then that defines what kind of monitoring or condition monitoring or data collection is necessary to implement what would be called smart systems. And then the output of those smart systems then needs to go into some kind of maintenance plan, and that maintenance plan is then executed in some way. So SKF is getting involved with all of these steps, and we'll follow through how that happens as we go through the presentation. But let's start thinking about this particular loop here, and going into that in a bit more detail. That's the process that some people would call from data to decisions. So whether you're in a smart industrial environment, whatever buzzword you want to use, industry 4.0, whatever, it involves taking data from somewhere somehow, collecting data on equipment, and then connecting that data to some computer, some system somewhere, then using that data to detect what's going on with the machinery, analyzing what the root cause of a potential failure might be, diagnosing, coming up with a diagnosis, and then eventually a prognosis. How long is it going to last? And then once you have that information, you need to reflect that into decisions and actions about what you want to do with it, whether you want to rebuild the machine or re-engineer bearings or change the operational movement of the equipment and so on. And also other data sources are involved as well, or should be involved. So that's the general process. And then what I'm going to do is follow how that process is manifested specifically with technology. So let's go first to the collect part, collecting data. And this is probably the biggest part in terms of complexity. We'll drill down into each one of the areas, but it's certainly the largest part. But first we need to decide, what do we collect? Now, from a rotating equipment point of view, which is probably in most industrial plants the biggest headache for maintenance and downtime, the machine condition indicators, the physical parameters that you want to measure to determine whether something's going wrong with the machine, they're dictated by the laws of physics, so they've not really changed at all in the 30 years I've been in the business. This is a pie chart from Frost & Sullivan a couple of years ago that broke down what the main condition indicators are used in plant condition monitoring are. And as you can see, vibration dominates the measurement parameter. Looking at lubrication, analyzing the chemical content of lubricating oil is probably the next biggest. And it's closely followed by thermography, so walking around the plant, using thermal cameras to look at hotspots and things that are standing out. The electrical systems particularly benefit from thermography because obviously they're not moving. And then there are other techniques like ultrasonics and other things which are used as well. But vibration dominates because it's the best parameter for detecting problems with rotating equipment early. The measurement of temperature is very, very common as well, but temperature is very much a measurement of last resort. By the time things are getting too hot, things are getting very close to failure. So vibration is the parameter that's used predominantly to provide an earlier warning than temperature or other techniques. One size does not fit all when it comes to the type of equipment that you need to collect that information. Moving back to your maintenance strategy and looking at the various criticality of equipment and the various potential failure modes that happen with machinery is a key decision tree in terms of what level of instrumentation you should be considering when you look at wanting to implement a smart maintenance program. So very much looking at the failure mode and looking at the time horizon of when that failure mode happens. So if the failure mode that's under consideration on the particular asset is a very short failure mode, then you need a certain class of equipment. So this typically tends to be on critical assets, turbo machinery, which is running very quickly. There you don't have time for a human to look at or a computer system to decide if there's a problem developing. You need to react instantly within less than 100 milliseconds typically. So there's a whole class of instrumentation, vibration monitoring instrumentation that's designed to do that job. So it's usually on very heavily instrumented equipment, things. Turbo power plant in the main turbine sets in a power plant would be one example, or the main pumps in an oil and gas plant, the main compressors in an oil and gas plant or gas turbine driven machines. So that's a whole class. And condition monitoring is of course used with those because the same source signals are used for long-term monitoring, but the primary job is to protect the machine, to shut it down if there's a high vibration so it gets linked into the control system. So I'm not going to cover that because that's more of a safety system rather than a plant monitoring system. So once the detection horizon of the problem is not short and is measured over days, weeks, months, and years, then there are different system solutions that need to be considered, and they're sized relative to the importance of the equipment. So if we look at wired systems, they are permanently installed data acquisition devices that are capturing vibration continuously, just like these guys, but they're not connected to the shutdown and do not perform safety functions. Instead, they're monitoring the vibration 24/7 and looking for changes in vibration that are indicating a mechanical problem and separating those changes from the normal vibration on the machine. And the normal vibration on the machine is in things like wind turbines, for example, can be continuously varying. So it makes it necessary to take the vibration measurements continuously in order to adapt for speed and load. And they also, the results of these systems are often connected to the control system of whatever machine they're monitoring. Then we move into the next level, which is again a permanently installed device like this, but instead of wired, it's wireless. There's a lot of wireless devices that have emerged on the market over the last five or six years or so, with many claims of being able to revolutionize your vibration monitoring program or your predictive maintenance program and eliminate your uptime and eliminate your downtime and so on. And they can go some of the way to do that, but it is important to understand that they're a wireless device, so that usually means they're battery powered, so they have a finite energy source, so therefore they need to take a periodic measurement and are generally only good for machines that have got a constant load and speed. But they can tackle failures that are starting to happen more often than collecting data with the next level down, which is portables. Now, the vast majority of condition monitoring data probably over the last decades has been collected manually because that's how the technology first really started and was much lower in cost to implement. And typically people walk around the plant taking vibration measurements on many different kinds of equipment, ranging from the critical down to the balance of plant. Typically on a monthly basis, maybe even a quarterly basis, and are looking for gradually building up failures over a long period of time, which probably represents the vast majority of mechanical failures on machines. And there's different levels of complexity of portable device that's used for that job. So we'll go into that in a little bit more detail in a minute. But this tree is important to understand in the fact that each one of these classes of device, from whoever's supplying them, have their own particular need, addressing particular needs in terms of the failure modes. So you won't you shouldn't try and use a wireless device for a machine that needs continuous monitoring. You shouldn't use a portable for something where the failure mode is going to be in days and hours, as opposed and you're taking a reading once a month with a portable. So there's which solution or a mix of all three is the best for your plant should be considered in this context. So let's go on to each one of those areas. First, we've got portables, and probably the biggest advance that we've seen in the last few years that would be considered smart is, instead of having dedicated, there's a general trend. I'll go back to this slide here. There's a general, most people associate vibration monitoring, portable-based vibration monitoring programs with this kind of instrumentation, which SKF has made for many years now. And they're very capable portable vibration analyzers and data collectors. And that the same tool can be used from someone that's relatively untrained just to simply collect data on a rote basis. And the same tool can also be used by a vibration analyst to do advanced vibration analysis using cross-functional phase and balancing and all sorts of high level. And probably what the major trend that we've seen that where smart devices are coming in is actually not requiring people who are using them to be so smart. In other words, the computing platform that was previously used for those high-level vibration analyzers is now being provided by these things, by tablets and by mobile phones, because the computing power that they bring are orders of magnitude higher than they used to be in bespoke instruments that people have used for many years. So the idea is they're getting increasingly simpler to use based on the enabler of this mobile phone technology. So the manufacturers of these high-level vibration data collector analyzers, such as ourselves, we're no longer needing to make the computer. Instead, the portable computer. Instead, we focus on the instrumentation for the front end, for the vibration analysis, for the vibration signal itself, because it's like any other system. Garbage in will produce garbage out. So the source of your data first is very important. And focusing on apps running on these computers to manage that information. And more increasingly now, rather than it being walked around and kept on the plant, more and more information is moving to cloud-based systems. So large software packages don't no longer need to be maintained. They can all be handled in the cloud, just as at home we're used to using now Microsoft Word provided by Microsoft, rather than having our own individual copy of Office on our own laptop. And then in the cloud, there's a combination of remote diagnostic services and self-diagnostics, if people want to use software as a service type of activity. And the remote diagnostic services are using a combination of people, which is still important, and automated AI and auto detection type systems. Let's move on to the next class of measuring wireless vibration. This product here is the SKF Collect IMX1, which was launched fairly recently. So it's an example of probably what the current state of the art is. It's by no means alone on the market in terms of wireless vibration sensors, but it's a good example. And you usually find that the sensors are getting smaller and neater and compact, but as I said before, most of them are battery powered, which gives limitations in terms of how often and how long you can take data for. And there's a gateway of some kind that's basically managing the connectivity to the outside world. So managing a network of sensors and then communicating either wired or wirelessly, either over Wi-Fi or a mobile phone network to the rest of the world. But probably one of the main innovations that we find with these wireless systems is the use of wireless sensor networks in a mesh. This graphic that's running here is showing how sensors are arrayed around the plant on machinery, and they're relaying data amongst themselves, because on an industrial plant you have a lot of wireless obstacles. So if there's clear line of sight, they can communicate directly. But if there's a large storage vessel full of liquid, or a big machine, or lots of big lumps of metal, they need to be able to communicate their data via their neighbors back to the source. So that means that this self-forming mesh network allows sensor information to be transmitted around a plant inside the pipe jungle, which is very challenging environment, much more challenging environment wirelessly than our homes that we're used to, where we can't get Wi-Fi signal up in the attic when our router's on the ground floor. In industry, it's even worse. So having this type of mesh networking is very beneficial. So here's some pictures of wireless devices. So there's the gateway before it was painted blue, located on a wall on a plant, and it's communicating, managing on that mesh, collecting data from these vibration sensors, and you can see the type of locations that they're put on. And this particular example shows the complex vibration signatures that are collected by these devices, and they give telltale signs in the vibration signature as to when there's a problem. And this is a particular example from one pump set where the we took the bearing out and did an analysis on what the size of the defect was that the device was picking up. And as you can see, it was just the first signs of subsurface fatigue on the raceway, which means this bearing, well lubricated, would have run for a long time, months, even years before failing. So that's the key, picking up defects, particularly in bearings from SKF's point of view, early. You don't want the defect in the bearing deteriorating to the point that the whole machine is vibrating and running around producing high levels of velocity measurements in RMS. That's getting too close to failure for comfort. So early detection is the key. It's not just vibration, as I mentioned before. You saw that what the other common technology is lubricating, monitoring the state of lubricant. Now, at the moment, analysis of the actual lubricant itself, the content, that's still quite expensive to do permanently installed. That tends still to be a manual selection and capturing of samples and off to some sort of lab, either locally or remotely, to see the chemical content. Although there are more and more things coming onto the market that can do that online, they're still quite complex to install. So from the point of view of failure avoidance, it's more of making sure the thing's lubricated properly in the first place, rather than what the condition of that lubricant is. So again, wireless technology is starting to be used now, where instead of having automatic lubricators that rely on simple spring systems to deliver a fixed amount, they can communicate the data wirelessly. That allows more sophisticated regimes in terms of how often and how much lubricant gets introduced into a bearing, and whether the system is operational, and which bearings have been lubricated well and which have not, in some kind of dashboard, and again, mobile phone implication. So wireless technology is being applied in that area. There are different communication networks that are used for different jobs. Again, it's just like the data acquisition. One radio solution doesn't fit all sizes. With the lubrication type systems, we use a LoRa communication, which is very, very long range, traveling signals across cities, but very, very low bandwidth. So it's only transmitting on, off, capacity number, something like that, across at a very low communication rate, because of course lubrication doesn't fail very, very quickly at all. It's very, very long term. So you wouldn't be able to use this same communication rate for vibration, for example, which has got much more data that needs to be transmitted. And then we move on to wired vibration, that last class. The instrumentation for this type of job is following all the general trends, and SKS products are no different. So things are getting smaller, more powerful. This particular device, our IMX816 product, is about the size of a paperback book. To do the same job when I first came into this industry 30 years ago, you would have needed electronics the size of a cabinet to do exactly the same functionality. So things are getting smaller and more capable as the years are going on. And it's important to understand, again, it's continuously monitoring data. So that allows it to adjust for variable speeds and loads on the inputs, usually taking in some kind of speed trigger, and maybe activating relay drivers to send I/O out to analog I/O out to the digital I/O, out to a control system, or using some sort of communication bus to communicate to the control system. So they're all the various ways of collecting the data, and we need to connect it. So there's various levels of connectivity. So if we take the wired example as the most complex example, firstly, there's local connectivity. So going into the local PLC or control system, using various protocols for digital data or analog digital I/O coming in. And then we then go off the device, either through a Wi-Fi connection or a local area network connection, or more commonly we're using today, we find, is the use of mobile phone connectivity to get to the internet rather than plant lands. The challenge of putting things on plant lands is there's an awful lot of security, and quite rightly, there's an awful lot of security and IT hurdles that need to be jumped onto. So for a very quick diagnostic job, where we need to troubleshoot a machine, for example, by placing sensors on the machine and an IMX in a portable form, perhaps, next to the machine, it's much more effective to run straight to our cloud using the mobile phone network. Once it's there, then of course there's cloud computing architecture, which allows remote diagnostic services, RDCs, to do failure analysis and communicate with the customer. And the customer themselves can also usually have some sort of editor or dashboard. We can also start looking at things locally by using the connectivity of these mobile devices to pull the same information that's up in the service down to something that's on the plant. Peer-to-peer connection, we do it for some of the use cases, but the vast majority of it is coming from the cloud, just like your mobile phone. When you send a picture to your daughter two feet away from you, it's not communicating directly phone to phone. It's going up into the cloud and coming back down again. And industrial systems are the same. And then often we find we need to interface the data that comes from these systems to customer systems of all sorts of different shapes and sizes. So that really usually requires an API, an application programming interface. That's just the name we gave our system, the interface to allow data to be transferred. This slide, I'm not going to bother going into the dirty details of it. It's for the people who like to know all about all the nuts and bolts of communications and protocols and so on. But the point being, we use the same, we operate in the same environment in terms of cloud computing and data transfer as everybody else, provided by the same giants of this technology, so the Microsofts, the Amazons, and so on. And the end result is, instead of complex data vibration spectra that nobody understands, it's much more clearly presented information based on the asset overview, the reliability overview of a plant, rather than the individual analysis results. That leads us on to the next step. Once we've got data connected and in the cloud, what do we do about detecting problems? So in the old days, it was just a simple alarm level from an overall vibration measurement, and it was up to a human being to look at that and decide whether that was a real alarm or not. Today, we still do that, but we also have much more in order to cope with the huge volume of information that we have to deal with. We have automated tools that are scanning the databases, looking for patterns, to look for anomalies in the vibration signature, to flag them to be looked at by someone. And there's different ways that's presented. This is just one screenshot of a simple trend, but there's quite sophisticated algorithms that are going behind to produce these alarm indications here. Once we've detected an anomaly, it's a necessary job to analyze and diagnose what the problem is. So analyzing the data and looking at what the problem with the machine is, and using the trends on the system to figure out what's going on. So there's a whole host of tools and different software packages that we use behind the scenes in that remote diagnostic center. Some of them are automated, some of them are not. That look at some very sophisticated ways that vibration behaves and how it works. And that would be a vibration analysis course in itself, lasting days to go and explain each of these. But the end result is we're looking at quite complex behavior because vibrations are complex parameter, and extracting very sophisticated diagnoses from those vibration signals. As I said, they can either be automated or manual, or a combination of both. So we have we model the machine trains and look for the various frequencies that are generated from the individual components, and have automated systems that tell us when there's a problem. The last step from data to decisions is, in this path at least, is the prognosis part. Now, the prognosis part is the holy grail of condition monitoring, and it still is. This is actually a report written by one of our colleagues in the Netherlands, so it's all in Dutch, so I won't bother you with translating it. But what it basically means is the human analyst really looks at the vibration information, looks at the vibration signatures, needs to know what the individual components are, and then from experience and a knowledge base within SKF, for example, could be with other companies as well, we know at which point bearing, at which point along the failure mode of a bearing, there's a rough indication of whether it's very close to failure or not. But it's so intertwined with the load of the machine, how it's the operation of the machine, how often it's running, how fast it's running, how heavily it's loaded, what kind of lubrication is there. These all factors which make actually predicting how long the bearing lasts a very difficult task. When we've seen many systems on the market that say, oh, we can predict the remaining 3 months left. Well, if the bearing's like this, it's got less than 3 months, it's got hours. But if the bearing's like this, it could be weeks or even years, depending on the lubrication. So it's not a simple task. And SKF have got a lot of R&D in progress to try and automate some of this, mainly because of the huge volume that we need to deal with. But also it requires quite complex models to do so. So that's where we're starting to enlist the help of AI, or artificial intelligence, where we're using computerized systems to hopefully do the whole thing. So we're doing parts of it, all of this already automated, but bring it all together in one artificial intelligence model is still a long a goal that SKF has yet to achieve, and most certainly the rest of the industry hasn't either. But they're all definitely on, the industry is definitely on its way of doing these sort of things. It's an AI system. Its job is to detect anomalies, diagnose what the root cause of the problem is, and then work out how long have we got, the remaining useful life, the RUL. And combining all the various sources of data that are needed to make an accurate prediction of remaining useful life is very application specific, and also needs a lot of data. So it's not just a lot of vibration data, but it's also a lot of process data from temperatures, pressures, flows that are probably going to come from the control system in that data collection part that I was talking about earlier. So definitely things going on there, and being able to predict the remaining useful life of a bearing is automatically is getting closer, but there's still a lot of work. The last part of that path is got actually very little to do with the technology. It's more to do with people and organizations and processes. You can have the best data collection system and analysis and diagnostic system in the world, but if it's not turned into good decisions and good actions by people, then it's useless. And that's where SKF addresses this part of the chain with a program we call Rotating Equipment Performance, which is a combination of the technology products you saw there before with services, both engineering knowledge services for bearings, of course, but also with lubrication, machinery diagnostics and condition monitoring, the technology of the instrumentation itself, and very importantly, application engineering for the bearings and other pieces of the rotating equipment. Not just the bearing itself, but the gearbox. SKF has 100 years of rotating equipment knowledge, and thanks to these guys, and as a result, we have quite a comprehensive mechanical engineering capability that we try to pull together into a single service offer that's bundled together for various different applications and functions, and linking it to a fee-based, KPI-based offer. So we're sharing the risks with the customer, but we're also sharing the benefits. And instead of it being funded by having to buy lots and lots of equipment under CapEx, it's instead worked out as a KPI-based monthly fee coming out of OpEx. So that makes things much more affordable to implement the whole process. Well, I said we take about 40 minutes, and my 40 minutes is up, and that is, in fact, my last slide. So we're happy to open the floor to questions.
Thank you very much.
Did any pop up in the chat?
Not yet, but now you are finished. Maybe someone will come up with a question. And otherwise, they can unmute themselves and maybe ask the question directly to you.
Nope. Clear as mud?
Okay, I think so. Okay, indeed, we were right on time. It's 40 minutes gone, so if no one has any more questions, I would like to let you know that we have 2 more webinars to come up next week. Tuesday, we will focus on the online communication tools, such as Bearing Select and Loop Select and all kind of software that's free available on the skf.com website, which can help you select the right bearings, select the right greases, select the right mounting and dismounting methods. Great opportunity to join that. And the last one before the summer break will be next Thursday, and then we will focus on the maintenance products. So the real tools that you need to mount and dismount bearings during the bearing life cycle. If you want to join them, feel free to visit our website. I will take care that you will have the link later today in the handouts. We have recorded this version, so we will share that with you later today, as well as with the handouts of the presentation. Until then, keep safe. Thank you very much again for your time, and hopefully we'll meet some other time during an SKF webinar. Thank you very much and enjoy your day.